So this time I'm going to talk about NLP experimental design, and this is something that I have covered for the first time this course. I didn't cover it in my previous course, but because this is a course aimed at people who are going to be doing NLP research, I figured it was probably important to talk about this, and also important to talk about this before we have you guys start working on assignment 3 and assignment 4, because the way you design experiments and basically choose interesting research questions is going to be pretty important for, what you decide to do in the following assignments. So hopefully this is helpful. I'd also love to have questions as always. So. Okay. There's a lot of echo. Maybe I can turn down the room mic a little bit. Can people in the room still hear me? Or yeah, it's fine. Is the echo better for people on Zoom? Okay, great. Cool. So I'm going to start out with this, which is a diagram that was adapted from the article on the scientific method from Wikipedia. And basically, this talks about the life cycle of doing experiments in any scientific discipline. And NLP is particularly an engineering discipline, so it shares a lot of commonalities with some varieties of scientific inquiry, like medicine, for example, because medicine also, you have a goal of building better treatments or things like this, and the more effective you can make a treatment, basically, the more you've succeeded. It has maybe a little bit less to do with other disciplines like physics, where the idea is to uncover some underlying reality, maybe with less respect to actually building something that's immediately useful, or pure mathematics or something like that. So nonetheless, all varieties of scientific inquiry kind of try to follow this procedure with small variations on the way they do things. And so what I'm going to try to do this time is go through each of these steps and map it onto NLP problems. And some of the stuff here we've already covered in the class, so I'm going to cover it briefly. Some of the things here we haven't covered quite as extensively. So the first thing I'm going to talk about is identifying good research directions, which is kind of on the top. And this starts with observation and questioning. And if we think about why we want to research, I kind of alluded to this before, but we can have applications-driven research where you do research because you'd like to make a useful system or make an already useful system work even better. And you can also have curiosity-driven research where you'd like to know more about, something. For example, in computational linguistics, you'd like to know more about language. Or in computational sociolinguistics, you'd like to know more about the world as viewed through language. You might also want to know more about the internals of how models work or other things like that as well. And NLP encompasses both of these areas, and you can even have you can do both at the same time. I do think it's rather important to not think you're doing one when you're actually doing the other. So you don't want to have applications-driven research that doesn't actually make anything useful, or curiosity-driven research that doesn't actually answer any interesting questions. So you might check yourself once in a while and question the direction you're working on to make sure that you're moving in a useful direction either way. So I just came up with a few examples of this, and in making these slides, I basically looked through the ACL anthology and other sources of NLP papers. It's very easy to find good examples of application-driven research, because this is a pretty large portion of the things that you would find in the ACL anthology, for example. For example, Peng et al. 2002, and one thing I should note is all of these are on the website as always. So if you want to look at the papers here, you can do this. So Peng et al. 2002 proposed a task of sentiment analysis. I bet some of you didn't know that there was actually a paper proposing sentiment analysis, 19 years ago. So you can go actually read it and see how they proposed this. It's one of the most influential papers in ACL history. Basically, they proposed the task of sentiment analysis because labeling articles with their sentiment would provide a succinct summary to readers. So they had an idea of people who would use the system readers of reviews, and this would provide something that's more succinct, which presumably would make it easier for them to understand. Reddy et al. Proposed a task of conversational question answering. So this proposes a new task because an inability to build and maintain common ground is part of the reason why virtual assistants usually don't seem like competent conversational partners. So the underlying assumption is that users would like virtual assistants to seem like competent conversational partners, and they're trying to resolve this issue. These two are proposing new data sets. Now, if we look at the ones that are proposing new methods, Graham et al. Propose a method of bottom-up abstractive summarization because neural network-based methods for abstractive summarization produce outputs that are fluent but perform poorly at content selection. So they have an idea of something that's wrong with the state of the art. It performs poorly at content selection, and they set out to fix it by proposing this method. And finally, this is what you talked about last class on Thursday. So Kudo and Richardson propose a method for unsupervised word segmentation because language-dependent processing makes it hard to train multilingual models, as we have to carefully manage the configurations of pre- and post-processors per language. So the idea was to make experimentation more useful for people who are working on these tasks. So to move from supervised to unsupervised methods to make this easier. So all of these have, I picked these as positive examples. There are also less positive examples where people are less clear about their motivations in application-driven research areas. So all of these have a very clear reason why they want to be doing the thing they're doing, basically. I also picked a few examples of curiosity-driven research. These are a bit harder to find, especially really good examples of them, but I have a few positive examples here. So Rankin et al. 2017 are asking the curiosity-driven question of what is the difference between the language of real news with that of satire, hoaxes, and propaganda. So this is based on detecting like fake news or satire or things like this. But this is, a good question. You can basically say if we can quantify the differences in real quantities that you can measure across these two things and say one is significantly higher than the other, then you've kind of answered that question maybe in an interesting way. Cotterill et al. Ask a question, are all languages equally hard to language model? So basically they ask whether a quote unquote language universal method actually works as well on all of the different languages. And they have some, tricky ways to do that. So this doesn't directly build a new application, but it might give some insights that would, make it easier to build applications in the future. And Tenney et al. 2019, I've talked about this already, but they quantify where specific types of linguistic information are encoded in BERT. So this is examining model internals. So I think in a way, this is kind of like a sociolinguistics, computational social science type question. This is kind of halfway in between modeling and like computational comparative linguistics, for example. And this one is more like understanding how models work and things. So these are all reasonable curiosity questions. Any questions about that? No? Okay, cool. So the next thing I'd like to talk about is how do we get research ideas? So I think a reasonable number of people have already come to office hours asking me this. So I figure it's a question that some people are grappling with right now. But basically, my suggested approach is there's basically two ways to think about this. So one way is to turn a concrete understanding of existing research's failings into a higher level experimental question. And this is what I like to call bottom-up discovery of research ideas. And I'm going to talk a little bit more about this in a second, but basically the idea is you take an existing model, like for applications-driven research, you would take an existing model and figure out where it fails, and then create a new, try to rectify those failings. Or for curiosity-driven research, you might say, okay, I know these past research results, but there's a clear unanswered question based on these past research results. Like, for example, maybe somebody did a survey on English or did a study on English, but it's not clear if that would work on other languages too. So that would be kind of one way of addressing the failings of existing research. This is a great tool for incremental progress. And I actually highly recommend it. Incremental is thought of as a bad word, but a lot of in some cases, in some research fields, but I'd say the majority of research is incrementally making the things that we already have better. And that's how we go from a system that's just a prototype but not usable to a system that actually is usable in many cases. Another way you can do this is move from a higher level question to a lower level concrete testing of that question. And this basically entails I call this top-down design of research ideas. And this favors bigger ideas, but the danger of doing this is that it can be disconnected from reality. So if you just have this idea, hey, wouldn't it be great if we could do this? That doesn't necessarily mean that it's going to actually be solving a real problem in the real world. Maybe the problem's already solved using existing methods.
One really good trick is you can take something that actually is incremental and make it look like a picture.
Well, a good trick is if you can take something that looks incremental and make it look like a big leap. It's the comment. Yeah, I don't. You could put it that way. I think actually. Let me see if I can. I think I'm going to have some examples of this later, but incremental progress doesn't need to be small progress. Also, is another thing. So, actually, one of my favorite ways of doing bottom-up discovery of research ideas is to do interpretable analysis or interpretable evaluation, like I talked about two lectures ago, and identify the areas where the model fails the most and fix those areas. So if you're fixing a big problem in models that causes a very large number of that covers a very large issue in existing systems, and that's not necessarily small progress. It can be big progress, despite the fact that you came up with it and despite the fact that it is incremental. So this is one example from my own work, which was very much motivated by bottom-up analysis of the failings of models. And essentially, near the beginning of neural machine translation models, we noticed that they were making lots and lots of mistakes on content words, basically. And the content words we'd have I come from Tunisia, and it was translated into I'm from Norway. So that's a problem. Or it'd be even more of a problem in a conversational system where you wanted to say, could you please send my luggage to Pittsburgh? And it says, could you please send my luggage to Tokyo or something like that. Basically what we did was we identified this problem, and then it's okay, well, what we can do is we can just bias the model to match the outputs of a dictionary. And because we can bias the model to match the outputs of a dictionary, the dictionary won't have these crazy things like Tunisia turning into Norway, so that improves the accuracy. And that helped accuracy a lot. The paper's also been cited quite a few times. It's maybe a positive example of bottom-up discovery. So as I said, like incremental is not necessarily a bad word here. Cool. For top-down discovery, actually, sorry, maybe I will get back to that later. I'm sorry. Yeah, I'll get back to that a little bit more later. So maybe I'll go into the topic area stuff first. Cool. So then a next thing in this diagram that we have here is researching the topic area. So this is to better understand essentially the current state of the understanding of the techniques that we have in the field. And I'm going to talk about research survey methods a little bit. And basically things that you can use if you've done a good research survey before. Some of this might be old information, but I think it doesn't hurt to hear my opinions, and then you can share any other ones that you have as well. But basically what I do when I do a research survey is keyword search to identify kind of like seed papers. And then I do a semi-random walk away from my seed papers to try to find other relevant research. And do this kind of while reading the abstract or the intro, and then reading the details of the most relevant papers here. So another thing that I often do when I want to learn more about a new research area is writing a short summary of the papers that I read, like 3 bullet points. What is the problem they're trying to solve? What is the methodology they use? How do they evaluate, and what are the results? So that also can be good because I personally, when I read the paper first, I don't necessarily read it super carefully. So forcing myself to write a summary like that can help me internalize and enforce discipline on myself to make sure that I actually did read the kind of most important parts of the survey of the paper. Yeah. How do you discover good keywords in the literature to describe a thing? This is a really good question. So like, if you have the wrong keywords, you might miss papers just because you don't know the right keywords. So I encounter it less and less often in the areas I'm familiar with, but I encounter it extremely frequently whenever I move a little bit outside of my area, because you don't know the technical terms in like in economics or something like this if I want to branch out a little bit. So I definitely still encounter it now. I don't know if there's a really good answer other than to try to find reasonably related works and then read them and see the keywords they're using and like branch out from there. So one of my suggestions, actually, I'll get to it here, is to go into a repository that hosts papers on the topic you're interested in. And for our case, the ACL anthology is or for the case of NLP, the ACL anthology is obviously the best place for this because it contains all of the prominent publication venues in NLP. You can also look on Google Scholar, but that's where you're going to run into the issue that you have here, basically. And for the ACL anthology, it covers many prestigious venues in NLP. It has ACL, EMNLP, NACL. These are kind of the most prestigious venues. And I would suggest that you look at maybe ACL, EMNLP, NACL in terms of conferences, and TACL in terms of a journal as a place to start your search. Another thing that you could do that I don't necessarily recommend is relying only on Google Scholar or only on Archive. And the reason why I don't recommend I recommend looking at the ACL anthology first is, number one, all of the papers have been peer reviewed here, so at least they've passed some threshold of like scrutiny by experts, so they're not completely, well, we hope they're not completely flawed after that. So they could be good positive examples of how to write a paper. Another thing is Google Scholar gives you papers in order of citation. Archive only gives you the papers from people who posted things on Archive. So they get, and there's no indication of quality. It's just anybody who posts on Archive can do so. So I've actually found that it's a lot more fun to read papers if I read them on the ACL anthology, because they give me a lot more variety, and it's not just all the papers about pre-training large language models from some like popular net company or something like this, because there's a very real bias of like what people pay attention to and cite, and so you get a lot more interesting things, I feel, when you get the full spectrum of the papers that people are publishing. If you're working in a different field than NLP, like if you're working on computational linguistics, which unfortunately, despite the fact that ACL is the Association for Computational Linguistics, it's quite the minority in ACL nowadays. Most of it's on NLP and not on computational linguistics. So you might look at other places like journals on linguistics, like Linguistic Inquiry or other things like this. Or there's also a Society for Computation and Linguistics, which is kind of designed to be for computational linguistics. Or if you want to go to psychology or machine learning, obviously you would be going to other venues as well. But nonetheless, the thing still stands. If you go to the place where top people in the field are publishing things, you can read papers there, and that will also help solve your keyword problem. So Google Scholar also allows for search of papers by keyword. I just randomly put in neural entity recognition. I don't know why I picked this, but that gives you some papers like neural architectures for named entity recognition, boosting named entity recognition with neural character embeddings. You can also do things like pick more recent papers if you want to find the more recent papers. And you can also follow a citation link to view papers that cite this one. Oh, another thing I forgot is that there's another service called Semantic Scholar that is actually pretty good. It gives you better summaries of articles. It also tries to predict whether articles are actually influential in their citations and stuff like that. So you might take a look at that too. So if you want to find older papers from the papers that you already have, you can follow the references. Not much to say here. You just find the references that look useful and follow them. And if you want to find newer papers, you can do things like search here, or you can search the papers that cited this one. So I definitely can say that having a pretty good idea of the research area is good. However, it's not the only thing, and I don't think you should necessarily feel obligated to read 1,000 papers before you start working. And it's not just because that would take all of your time and then you never work, but it's also, there are some downsides to it as well. So surveying extensively before doing research helps prevent you from duplicating work. So maybe somebody already built exactly the tool that you wanted already, so you don't need to do it again. Another thing is by having an idea of the experimental techniques or the modeling techniques that people use, that increases your ability to answer the research questions that you want to answer. But at the same time, it constrains your thinking. And there's a reference in the lecture notes or the lecture references by Viri in 1994 called How to Build an Economic Model in Your Spare Time. This was actually recommended to me by Chris Manning a few years ago. And basically the idea is, it's by a Nobel Prize winning economist who says, what you don't do when you want to come up with interesting research ideas in economics is go and read economics journals. What you should do is you should read the newspaper. Because the newspaper is where they tell you about like what's happening in the world, what current events, and then that will stimulate your thinking and say, hey, I wonder like what are the implications of this event for economics? This is going to be really boring because I'm not an economist, but you know, like what are the implications of COVID on like economic theory or something like that. So if you want to have an analogy of what that would look like in NLP, you know, like look at the world around you, look at the language usage that you're using, look at the usage of language on Twitter, or think of the thing that you would really like to have, like the website that you would really like to have but doesn't exist right now. Maybe that's a good direction for a research topic that you should be pursuing, and that might give you more creative ideas than looking at the ACL anthology, right? So it's kind of on both sides, you know, it's like, if you read all the literature, spend all the time on your literature review, then you might not branch out quite as much. Cool, any questions there? Okay, great. So next I'm going to move on to the form hypothesis part, and this is making your questions a little bit more concrete, and also forming ideas about how your experiments are going to go. So we have a research question. It could be one or several explicit questions regarding the thing that you want to know. One thing about research questions is very often things like yes, no questions are better than how to. And the reason why is because the next thing that you want to do is you want to form a hypothesis, what you think the answer to the question may be a priori. And this hypothesis should also be falsifiable. So if you get a certain result, the hypothesis will be validated. Otherwise, you can't. You often can't completely disprove a hypothesis, but you know, if you for many questions, for example, curiosity-driven questions, you can get negative evidence towards that hypothesis being correct. So here are a few examples of curiosity-driven questions and hypotheses. The one that I mentioned before, so are all languages equally hard to language model? And the hypothesis that they had with respect to this was that quote unquote universal language modeling techniques actually aren't universal, and some languages actually are harder to model than other languages. So that they expected that this hypothesis would be correct, and the way they could verify it or disprove it is if they ran a language model and got basically the same results across languages, or if they got significantly differing results across languages. Another one is what makes a particular podcast broadly engaging. For example, they would like to know when a podcast is viewed as engaging or not. And they have some hypotheses. So fewer filler words and disfluencies, more emotion are things that have been cited in previous like anecdotal accounts or best practices guides for creating podcasts. But they would be able to then verify this by extracting features that correlate to these things and testing whether they're useful in predicting whether a podcast gets a lot of viewership or not. Sorry, actually, this is the wrong citation, but you can look for like podcast in the citations and you should be able to find. We also have application-driven questions and hypotheses. So this is an example from my own paper. This is something that I actually kind of wish people would do a little bit more, which is explicitly lay out the research questions that you're attempting to answer in your paper. So in this case, this was more of an exploratory work. So we had lots of different questions, like is the behavior of pre-training affected by language families and other linguistic features of source and target languages? Our hypothesis with respect to this was basically yes, we would expect there to be a significant difference there. Do pre-trained embeddings help more when the size of the training data is smaller? Hypothesis is pretty clearly yes. We had some motivations for this. How much does the similarity of source and target languages affect the efficacy of using pre-trained embeddings? We didn't expect this to be much, but we didn't have a strong intuition, et cetera, et cetera. Another example is like, they didn't actually phrase this as a question, but they say, so far the research question, oh no, sorry, they did. So far the research question of whether and how contextual information benefits end-to-end speech translation has received little attention. So they didn't say this is our question, but basically the implicit question is, will contextual information help? And their assumption is that it probably will, but they need to verify that. So one thing I'd like to warn you is having as your one and only research question for your paper is, does X make Y better, where your hypothesis is yes? This is a pretty obvious research question, and one that I think can be an overarching research question for application-driven systems, but it's also very indirect. And what I mean by indirect is that if the answer is no after your experiments, then how would you know what you did wrong? And if you think about it, usually you have an intuition about why the answer is yes, right? You're not just doing a random search over the space of like various different model architectures or training methods that you could be using. If you are, then neural architecture search and other computers are coming for your jobs. So you know, I'd like you to use a little bit more intuition than that. So because you have an intuition about why X will make Y better, can you think of any other research questions or hypotheses that are in your reasoning chain for why X would make Y better? So for example, pre-trained embeddings do, that's a little bit more fine-grained, but like the indirect research question about why our research question on the left here, this is a paper about incorporating pre-trained embeddings into machine translation models. And we could have a less interesting research question, which is, do pre-trained embeddings help neural machine translation models, where our hypothesis is yes. But our underlying intuition about why we think that answer is yes is because they help alleviate data scarcity, or they help decrease the disconnect between source and target languages or other things like this. So we can derive these like sub-research questions based on the bigger research question because they're in our reasoning chain for why the answer for the research question is yes. Yeah. Right. So you can have intermediate results that test your intuition. So that's a basic takeaway. Any other questions? Okay. Okay, so now I'm going to talk a little bit more about testing with experiments. And so running experiments, basically, in order to do this, you'll need to find data that help answer your research question, run experiments and calculate numbers, and calculate significant differences between the numbers and analyze effects. So I've already talked about statistical significance calculation. Hopefully people remember that from the beginning of the class, but I'll talk a little bit more about the first two. So an important thing to do here is to obtain test data. And in many cases, this is as simple as finding an appropriate data set. Or when I say simple, it's not actually that simple, but you know, you can find an appropriate data set, such as one that was used by related previous work. If you're answering a new question, you have two choices. One is you could try to repurpose other data sets to answer the new question that you're trying to answer. Or in other cases, you'll have to create your own data set. And all three of these approaches are equally good. Obviously, the first one's easier than the second, which is easier than the third. So one good place to find data sets is this thing, Hugging Face Datasets, hence the name. So you can go here. I mentioned this early in the class, but I wanted to reiterate them here. Another thing is there's a famous conference called LRAC, the Language Resources and Evaluation Conference, where lots of people create and release data sets. And they actually have a list of shared language resources that you can go to. There's also papers with code that is another data set list, maybe more similar, with more overlap to Hugging Face data sets. I think the nice thing about these two is there's some overlap between them, but they cover kind of different communities. In other words, Hugging Face dataset covers more like prominent, high-profile data sets, and LRA will tend to cover more niche data sets that nonetheless could be useful to answering your research questions. So you can look at both of those as potential resources. So another thing is if you need to annotate data yourself, oh, sorry, go ahead. Yeah, yeah, so that's a good question. How to keep track of research and like data sets or research papers or knowledge or stuff like this. So when I was a graduate student, what I did was I actually had papers filed away in like folders and stuff like this. It's not that computers didn't exist at the time; they did. I'm not that old, but I feel like reading things on paper just works better for me mentally, and other people might not be that way. I don't actually have a good PDF filing system. I have docs of research surveys, for example. Like when I do a survey like that, I will. Yeah, actually, when I do a research survey on a particular area, what I do is I have like to read at the bottom, and these are just like links, and then I have read, and this is like title and bullet points, title and bullet points and stuff like that. So that's more or less what I do. It's not very like, I don't use Mendeley or like any of the tools that some people use to organize things. So other people might have better ideas than I do. Yeah. Yeah. So it depends. That was a very good question. Like, how do you, when you repurpose a data set, how do you deal with the idiosyncrasies from it being from a different task? And actually, it's not just that. When you're repurposing tools, you also run into this problem where the tool was originally designed to do a certain thing, which is like 80% overlap with the thing that you actually want to do. I don't know if there's one size fits all solution, but for example, if you have a data set where the annotations are more coarse-grained than the ones that you actually want, you can do annotation, but like rely on the previous annotations. If you, for example, want to do, like Bob is going to talk about syntax over the next couple things, but let's say you want to do dependency parsing on English. There are rule-based converters that can take a phrase structure parse of English and convert it into a dependency parse. So if you have two like different ways to describe data and they can be converted into each other, or one can be converted into the other one-to-one, then you can do a deterministic conversion and get what you want out of it. So I think it really is quite case by case though, and there might be cases where you can't do it without significant extra work. So. One thing though is you can put annotations on top of another data set. So sometimes even gathering the linguistic data, like the English or the Chinese or whatever, is the hard part. And that's another thing that you can do. You can take the linguistic data that they gathered, but put annotations on top of it. Cool. Any other questions? Okay. So this reference up here is a guide of best practices for annotating data. So this goes into a lot more detail than I'm going to go into here. But basically, when you're annotating data, you'll want to decide how much to annotate. You'll want to sample appropriate data, sample appropriate linguistic data. So basically the inputs to your model. Create annotation guidelines, hire or supervise annotators, evaluate quality, and other things like this. So how much test or development data do you need to answer a question? And this is like one of the major questions that people ask me when they want to create a data set. And the good thing is you can actually have a pretty clear answer. You can have a pretty clear answer for most NLP experiments. So basically, like we have a research question that we would like to answer, right? So we've already devised a research question. We have our hypothesis. So we want our data set to be large enough to allow us to answer this hypothesis. And specifically, because we want to be sure that whatever effect we find on our data set is real, we'd like it to be large enough to have a statistically significant difference between methods. And so how can you estimate how much is enough? And this can be through a method called power analysis. And there's a really nice survey of power of like statistical power in NLP in this Card et al. Paper. But basically, power analysis, what you do is you make an assumption about how big the effect between two settings is. So to give an example, you might say, well, I want to compare models. I think that if I get a better model, the better model will increase accuracy by about 3 points, or by 2 points, or 1 point, or like I care about accuracy differences that are at least 1 point or 2 points or 3 points larger. And once you do this, given a particular effect size and a significance threshold, you can use an analysis, a power analysis, to determine how much data is necessary to get a significant effect in most trials. And basically, the more statistically significant you want a result to be, like basically the less probability you want it to be by chance, and also the smaller the effect size, the smaller the differences you want to discern, the more data you need. So like, let's say I want to determine a 0.5 accuracy difference with 0.01% probability. Like I want to be 99%, basically 99% sure that the difference is real. Then you're going to need a larger data set than I'm okay with only discerning a 2% difference and a 0.05 significance threshold. So just to give a brief sketch, I won't go into the details because actually the details depend on which statistical test you're using. But for example, if we were using the bootstrap test like we did before, you could make certain assumptions about you could make certain assumptions about how difficult a particular example is, and then how well a particular model will do on examples of different difficulty, and then run a simulation to determine how large a data set that you need to find the difference. And then if you make other assumptions, like let's say mistakes between two models are independent of each other, then that will make it harder and other things like this. So this is kind of vague because I don't want to go into all the details here, but are there any like high level questions? Yeah, exactly. So how do you make, that's a good question. How do you make the assumption about effect size? Basically, in application-driven scenarios, it's more about what difference you think is interesting enough to care about. versus how big the effect is. Sorry, versus how big the underlying effect is. So like you're going to be creating a new model. That model is going to be making some improvement. How big of an improvement is interesting enough to care about? So to give an example, maybe on sentiment analysis, you really don't care about an improvement that's less than 2%, because the difference in 2% is the difference, like it would cost you more to implement that. Like, let's say you were a business, it would cost you more to implement that new system than the gain that you would get from having a 2% increase or something like that. However, if it's like ad targeting for Google, maybe you care about 0.0001% because that would earn you $1 billion or something like that. I intentionally don't work in ad targeting, so I don't know the actual value, but so the size of an interesting difference is the important thing in application-driven areas. In curiosity-driven areas, or something where you like want to measure whether there's a difference, you just kind of have to guess, I guess, how big you would expect the difference to be. So, for example, if I said how much more, like let's say I had a hypothesis that fake news tended to use more frequent words than real news. And the reason why I would hypothesize that, I don't know if this is actually true, but like the reason why I would hypothesize that is maybe real news tends to be written by more professional journalists and they know bigger words. Just like, that's just a guess. I have no idea. So then the question is, how large is this frequency effect? What would be the frequency? What would be the difference in average frequency rank between the two? And I honestly have no idea, so you just have to guess. You might make an educated guess, but it might be difficult in a situation like that. So you could also make a very conservative guess and collect enough data that even if it was a very conservative guess, you'd still find a significant effect. Cool. Any other questions? Yeah. Would it be okay to hold your statistical significance threshold constant and see how much data you would need to collect? Yes, definitely. And in fact, you very often hold the significance threshold to 0.05 for no reason other than the fact that everybody else is doing it. But yeah, so you could definitely do that. Cool. Okay, next question. How should I sample data? This is a question that I kind of wish we thought about more. I think we are starting to think about it more as a community, but maybe still not as much as we should. So if you're building an application that people are going to use, you want to make sure that your data covers the domains that you would like to cover. So if you're going to be building a translation system that is built for Amazon, and one of the major things is translating reviews, you want to make sure that you have lots of reviews. However, if you're still Amazon, but you want to deploy something on AWS, who knows what AWS users are going to use translation services for? So then you need to have like much broader domains, for example. Another thing is language varieties and demographics of users. So like, let's say you're building something for a social media site. You definitely don't want translation data that's only from one set of your users, because then your translation system would fail on social media posts from other sets of users. So you collect only American English, it's not going to do very well on Englishes from other places in the world. So there's an excellent paper on this called Data Statements for Natural Language Processing by Bender and Friedman. And they give a bunch of guidelines for what you can think about when you create your data set. I actually think these are still insufficient. I think there's other things that you could be documenting in addition to these, but this is a good start. So things like curation rationale, language variety, So like, for example, what dialect or where it came from, how old are the people, what dialect, where it came from, what language is it in the first place, speaker demographic. So what demographic are the people who are speaking, gender, age, race, etc. Also annotator demographic. So I found this interesting, but it makes sense. Like the people who are annotating the data, are there any potential biases incorporated through this? Like, for example, maybe people who don't speak, a particular dialect might be bad at annotating sentiment from the dialect. Speech situation. So are people speaking in an informal setting or formal setting? The thing that I think is most insufficient from the data statements is text characteristics covers like everything else. So it's like, what domain is it? Where was it derived from in terms of where was it derived from in terms of source? Also, what year is it from? There's lots of other things packed into this. For speech, recording quality. So did you get it from a nice microphone or a bad microphone? Other comments. So it gives you some guidelines to things to do. How popular is it? Not very. It should be more popular than it is. And in fact, we're trying to like collect data, and it's actually frustratingly difficult to collect stuff like this. And I don't think any data set has, or I think very few data sets have all of the things listed here. And if you take this and the union of like some of the metadata that Hugging Face data sets collects, I don't think like any data set has all of those documented. So. I think there is, and I think in particular with respect to speaker demographics and being sensitive to that, with respect to not just assuming that everything's in English, but considering multiple languages, I think there's a positive trend in that direction. So yeah, I do think so. So another thing, there's a lot of, oh, sorry, I see one other. Is including statistical significance emphasized nowadays? I feel that many papers only include metrics, but not statistical significance when comparing different methods. Do they just implicitly assume statistical significance based on data set size? That's a good question. I don't think they implicitly assume statistical significance based on data set size, and you shouldn't either. So if you see a paper without statistical significance tests, you shouldn't assume anything about this being a real result. Period. Okay, annotation guidelines. So the next thing you should do is you should come up with guidelines for annotating your data. And the way that you can do this is, the first thing you should always try to do is annotate yourself. So if you're doing any sort of data annotation, and you can create annotation guidelines and iterate. There's no like 100% correct way to do things. There are some good examples. But my suggestion is that you basically do things like coming up with a first pass annotation guideline. So this is an example from the Penn Tree Bank parts of speech, and it says something like adverb. This category includes most words that end in ly, as well as degree words like quite, to, and very, post-head modifiers like enough and indeed, and negative markers like not, and never. So this gives you a general idea of what the class is like. And then you have other examples, adverb comparative, and things like this. But in addition to this, you can have a example of difficult cases. So this is an example of confusing parts of speech. So this section discusses parts of speech that are easily confused and gives guidelines on how to tag such cases. And they have a huge list of these, like comparing between CC and DT, which is the coordinating conjunction and the determiner. and it says like either can be, I didn't intend this way, but either can be either of them. And so it has an example of a determiner. It also has an example when it's a coordinating conjunction, and you can explain the difference with examples. Great. So next, on to hiring annotators. So let's say one thing that you can do is you can annotate yourself. This is an option for very small scale projects. You're probably going to be better at annotating than anybody else who you would ask to do so. And however, one thing you should be careful of doing is annotating when you're evaluating your own model, because you might have an implicit bias towards liking your model. You know, you spent a lot of time raising it and feeding it food and making it beat soda. One thing that you can do to make yourself a little bit less impartial, or a little bit less, you know, biased, is basically randomizing the order of models. Like if you're doing text generation or something like that, and doing evaluation that way. Still, you might be able to identify your model's outputs and like them implicitly more, even if you don't intend to cheat. So it's a good idea to try to get somebody else to do it. Another thing you can do is colleagues. So it's perfectly okay to have friends or other students or coworkers help you out with things. It's especially good if you don't tell them what your experiments are about beforehand, but that's not a necessity. So you can ask people to help you out. Say, hey, I'll buy you dinner, or buy them Amazon gift cards. If you're working on a research project that has some funding, usually the person who has the funding will be happy to support this. I always support this for my students. So, that being said, dinner is not super expensive. Actually, that's the thing I did for my first research project, except it was beer, but I don't think I can recommend giving your friends alcohol for annotation in my class. Another thing you can do is online. Mechanical Turk is the most famous way of doing this. It has a lot of advantages. However, for many skilled tasks, sometimes you want somebody who has specific skills. Like, for example, we wanted an example where we had somebody who spoke both Portuguese and Python. And it's going to be a little bit hard to find a Portuguese-speaking Python programmer on Mechanical Turk. So what you can do is you can go to freelancing websites or other things like this. You can also find like bilingual speakers or translators or stuff like that quite easily. For crowd workers, you can definitely go through Mechanical Turk. There's other alternatives. The advantage of Mechanical Turk is it's very easy to scale up. So you can scale up to like hiring lots of people very quickly, and so that's definitely an advantage there. One important trick is to hire people for a small job first to gauge their interest and effectiveness, and then hire for a bigger job. So you can hire them to do, on Mechanical Turk, you can hire them to do $1 worth of work or $5 worth of work first. See if they're actually good at doing this, and then hire them to do $100 worth of work later, or something like this. And so this is really important. If you hire people for a big job and then fire them later, this really hurts your reputation on crowdsourcing sites, possibly for good reasons. So it's better to hire people for a small job, you know, give them money for the small job that they did, and then just not hire them again. Cool. Any questions here? Okay. Assessing annotation quality. So one way you can do this is through human performance. And basically what you do here is you measure human performance with respect to the same metric that you would be measuring machine performance by. And this could be, you know, anything like accuracy or blue or rouge or BART score or whatever else. So what you do is you double or triple or quadruple annotate some data, and see what the score of the human is with respect to all of the other humans. And so this is good because this also makes human performance directly comparable with machine performance. And so you can say, well, human performance is here, and then I have my current machine performance here. So you'd like to improve here. Yeah. How do you know which human to trust the most? So this is not, actually, maybe human performance isn't the best way to say it. Human agreement is a better way to say it, because it's more like agreeing how well people agree. If you have human annotators who you know are probably better than like you, for example, then you could use you as the gold standard and use other people with respect to that. Yeah.
One interesting thing is that you can often take the annotator disagreement as kind of the threshold for machine performance too. So the machine performance as well as the annotator agreement is kind of amazing.
Yeah. I think I might have something about that. Actually, I don't have something about that. So Bob's point was good, which is that you could treat the human performance as kind of a ceiling for machine performance. Unfortunately, a lot of the time this isn't true anymore, because a machine, well, so number one, Google translates probably better than you at translating Tigrinya, unless you speak Tigrinya. So I don't think anyone in here speaks Tigrinya. So Google Translate's still really bad at translating Tigrinya, but you know, it's a task that most humans cannot do. Even for hard tasks, where the human should be qualified, it depends a lot on their motivation, right? So like an underpaid mechanical Turk worker is going to be pretty bad at a lot of tasks that machines are used to.
Like, you know, on real annotation tasks, even with good people have some facts of disagreement.
Right.
So if you have a parser with 98% accuracy, that's as good as people in some cases.
Right. Yeah. So, and it's as good as people in a certain situation. I guess what I want to say is, like on English to Chinese news translation, there was a very famous paper by Microsoft in 2018 or 2019 or something like this. It basically said English to Chinese machine translation is now as good as human translators, which is interesting because if you look at the outputs, they're still not very good. So the human translators are also not very good. And the reason why the human, they're not horrible. They're like quite good, but they make mistakes. And the reason why they make mistakes is because if they were translating this for the New York Times and they had a copy editor, they would not make that mistake because their job would be on the line. Here, they were paid 10 cents a word to translate data that they knew was for a machine translation experiment. So they're like, sure, I'll do this, but I'll try to do it fast enough to not get fired. You know?
Also, the metric may not capture everything that human beings care about.
The metric might not capture the thing human beings care about. This was human evaluation, according to professional translators, so it was a pretty good metric. Yeah. So, but basically, like, I agree that in some sense, human performance is kind of like, you could kind of view it as an upper bound, but it's not actually, like, especially now that systems are so good. So, yeah. Oh, that's a really good question. Is it common to limit human performance in a way similar to machines to see if that has an effect? Sorry, my computer's about to run out of battery. I don't know why. Okay, there we go. Crisis averted. So yes, that's really interesting, and there are studies like this. I can show you one of my favorite ones. And this was actually done a while ago before machine translation was anywhere near as good as human translation. So this is a paper called Evaluating Machine Translation Systems with Second Language Proficiency Tests. And basically what they did, it's a short paper, very easy to read. But basically what they did was they have 3 settings. They have a setting, and their evaluation metric here is whether middle schoolers can solve Japanese middle schoolers can solve second language proficiency tests in English after translating them into Japanese. So basically the idea is you take the English proficiency test, but you translate it into Japanese and see if they can solve it. So I think the experimental setup's also interesting. But they measured 3 systems. They measured G and Y. Y is Yahoo, G, you can guess what that is. But they have a human with all of the context and a human with only sentence level context. And so basically they limited the human to be the human translator to only look at sentence by sentence. And what you can see is that the human translator with full context, like totally is way, way better than the machine translation systems. But the human without context is like nearly equal to the machine translation system. So this is definitely something you can do, and it can give you interesting comparisons. I saw another hand. Oh, that's a really good question, and I don't know if I actually have this on the slides. Maybe I'll get to that in the data analysis section. I'm running a little bit low on time, so I'll try to go through that. Was there a question there? Yeah. Yeah, time limits would be another interesting way. Yeah, great. So basically, the kappa statistic is another way to assess annotator quality. It basically looks a little bit like this, where PO is the observed agreement and PE is the expected agreement. The idea behind this is accuracy if your expected agreement between like tags is very high, like 95%. Like let's say you're doing toxic language detection where most things are not toxic. Your accuracy might be very high, but your system might be very bad. So basically the kappa statistic is a way to control for this. And you can find more information about this if you're interested. If it's low, you may need to revisit your guidelines or hire better annotators or rethink whether the task is possible in the first place once you've done both of those two. So if you do a really good job on this, then I'd be much more convinced that human performance is actually an upper bound to machine performance. For obtaining training data, oh, wow. I'm sorry, I have many more slides than I expected here. What shall I do? Okay, I'll cover as much as I can this time, and then maybe we can figure out what to do. So for training data, more data is usually better. But actually, it's been pretty impressive how good performance we can get with few shot or 0 shot transfer settings and pre-trained models with things like prompting. So you can actually, you might not need as much data as you would have traditionally thought you did in order to solve the task that you're interested in. Another thing is you can do even better with intelligent data selection methods, such as something we call active learning. So basically what active learning is we have labeled data, maybe a very small amount of it, and we do training, we create a model. We have unlabeled data, from this unlabeled data, we do some selection of data, we annotate it, and we add it to our training data and go in the circle like this. With the idea being that once you have an initial model, you can do much better at training a system than you would do, or you can do much better with selecting data that would be useful for training the system than if you didn't have the model a priori. So to give another example of why you might want to do this, let's say you had a fully supervised classifier like this, where you annotated all of your training data. If you annotate just part of your training data, just 6 examples, you might get a poor classifier. But if you annotate the right examples, you could annotate 5 examples and get a really good classifier. So that's the basic idea behind active learning. There's a couple of fundamental ideas here. One is uncertainty. We want data that are hard for our current models to handle. These can be low certainty samples close to a classification boundary, maybe ones where your model says there's only about a 50% probability of getting them right. They can also be the samples where multiple models disagree. So this is something called query by committee, where you train multiple models and see where they disagree. Another fundamental concept is representativeness. So this is where we want data that are similar to data we are annotating. This can be similarity in surface form. So in NLP, we can look at the actual words and say, hey, it looks like this word or sentences with this word in it are hard. It can also be similarity in embedding space. So you can measure the embeddings and try to get good coverage of all of the embeddings that exist in your embedding space. I would suggest maybe starting out with this survey by Settles, and then I have a few other references in the references if it's interesting to you. And basically, what you do with active learning is you start out with very little training data, and you gradually increase the amount of training data that you have, and hopefully some curve that uses active learning, like this full black one here, does better than just random sampling of the data, which is this dashed one here. And this isn't guaranteed by any means. In fact, it's provably impossible to come up with an optimal active learning strategy, but under some assumptions, such as the fact that labels will be clustered together or things like this, you can do much better than that. With respect to running experiments, a few tips I have. One good idea is to modularize each step of your experiments. In particular, when I don't get to run as many experiments as I would like nowadays, but when I did, the one thing that I would do is I'd always have a directory in, directory out structure for different steps of the experiments. And what you can do is you can do things like name directories by parameters. So you could have your transformer layer 8 node 512 dropout 0.5 label smooth 0.02 directory. And this would be your training directory, and then you can change whatever other things. You could also do this for pre-processing. So if you have 5 different varieties of pre-processing, you pre-process into those 5 different directories. And then you would have like sentence piece 32K, layer 8, node 512, and stuff like this, where if the directory already exists, you don't rerun the processing with those parameters. Yeah. Well, so for example, like what if you had pre-processing? So that's one step. Then you have pre-training. That's the second step. And then after that, you have fine-tuning. And basically, the pre-training step will always be influenced by the pre-processing of the data. So the directory name would be longer, would have more parameters in it for the pre-training step. And then the fine-tuning would always be affected by the pre-training. So the fine-tuning would have the data parameters, the pre-training parameters, and the fine-tuning parameters in it. So it basically gets longer and longer and longer and eats up your terminal, but it's a good way of managing experiments and stuff. And there's actually a tool that allows for, there's several tools, but this is one in particular that was originally made here at CMU by a PhD student called Jonathan Clark, and has been revived by my PhD student, Patrick Fernandez. So if you're interested in kind of setting up things automatically with better versioning and stuff, you can do this too, but I always just use directory names and stuff. For evaluation, I already talked about this a lot in previous lectures, you know, evaluating NLG models and stuff like this. Train on train, tune on dev, eval on test. There's lots of different metrics like accuracy, precision, recall, F measure, NLG metrics. Extrinsic evaluation, so see how well things work on downstream tasks and make sure you do statistical significance. So I think I've covered all of these, so I won't cover them again here. With respect to result reporting, one idea that is easy to say, harder to do, but still maybe useful, you can plan the results section of your papers in advance. One good thing about this is if you are trying to make a claim about a particular phenomenon, this allows you to make sure that you've actually supported that in a convincing way. It also allows planning for kind of a best case scenario where all of your experiments go according to plan. So you just assume that all of your experiments worked really well and then plan the next experiment, and then that can give you a path to being finished with your paper or class project. Another trick that I do is using result generation scripts. I personally, for all of my experiments, tried to generate paper LaTeX directly from my log files or CSV files to import into Google Sheets. So I would update Google Sheets with the CSV every time I got new results. This is efficient and minimizes errors, but it also allows you to preemptively plan experiments. So I would plan which tables I wanted to generate in advance. And then as my experiments finished, I got to see the tables become more and more complete, which felt really good. It's like only 3 more nans in my table here. So I'm almost done. Another thing is about computational resources. So online resources, you're using AWS. There's also Google Cloud and Colab, TensorFlow Research Cloud. I'm actually talking with a few other cloud providers to see if I can get coupons for like large memory GPUs that people could use. So that'd be great if that works out. You can also build your own. There are commodity GPUs like the RTX 3090 or the A6000. These will run you on the order of like $2,000 and $4,000. So it's not cheap, but I've calculated, and they pay for themselves in about 70 days worth of usage on Amazon. So, you know, if you're going to be running constant experiments for more than 70 days, maybe it's not a bad idea. So for data analysis, I'm just going to go through all of these. I only have 2 slides left, I think. So for data analysis, I talked about the interpretation lecture, looking at the data, of course, and we had quantitative and qualitative analysis, model explanations. One important question that I just got, which is how do you control, how do you control for variance according to what time of day it is? You give your job in the evening in the US and you get lots of people in India. But you give the job in the morning in the US and you get lots of people in the US, for example. So maybe that affects the annotator demographics in some way. One way you can control for variables like this is using fine-grained quantitative analysis to make sure that this isn't causing a significant difference in your results. Another thing you can do is there's something called linear mixed effects models. And if people are interested in this, I use these for a lot of the experiments where I collect human data because it's very hard to collect lots of human data. And what these allow you to do is they allow you to control for quote unquote nuisance variables that are variables that you think will affect the results, but you don't actually want to be measuring. Like, is the person, how long has the person been annotating? If they annotate more, they'll get faster, for example. So that's something that you can control. Okay, final thing, which I'm glad I relegated to not this lecture because I'm out of time, is how to write a paper. This is a great tutorial that I learned a lot from. There's something called How to Write a Great Research Paper by Simon Peyton Jones. And basically it tells you how to write your story for your paper, how to lay out your thoughts, what organization you should use, and things like that. So I won't reinvent the wheel, and I'll just forward you to this. So, I'm happy to give advice if you have fine-grained advice beyond that.